I wrote an article more than 20 years ago, which I called The Drip Analogy to Quantum Events. What it's trying to explain is why people are looking at quantum events a little bit wrong. So in this case, what I've imagined is a bucket of water, it's full to the top, and we've got a tap dripping. When the drip hits, a ripple goes out from it. Of course, it gets weaker and weaker further away it gets. When it hits the side, it will bounce off. So there will be wave patterns from previous drips bouncing about, and the drips may be not perfectly regular, that doesn't repeat itself. But there's patterns of waves, and at certain points on the edge, wave patterns will converge, and the drip will fall over. Now, what's this got to do with quantum events? What I'm making clear here is the drip coming in is the emission of energy, which is called a quanta. A quantum of energy is being released by some atomic structure. In this case, it's being released by a tap, but we don't worry about that. It's some energy being released, and it spreads out in the electromagnetic field. At this point, some energy is converging on a point, and the drip going overside represents the energy being absorbed by some other atom or atomic structure. Although the drip falling in, we can see a wave that travels from there to there, and we can say it causes a drip. It's not the sole cause. Although the drip in and out are causally related, they're not the same drip. The drip that fell in there was lost. The drip that came out of here just came from the water there. But the wave that travelled between them is a causal factor in what happened. And although the energy in and out are nearly equal, it's not the same energy. The energy of that one was dissipated all over. Some of this energy came from past drips that were bouncing around. So this is the misunderstanding that's happened in quantum physics, that people think they've tried to connect. They've seen that light got emitted there, and at the speed of light later it got absorbed here. They think it's the same energy. It's not the same energy. It's causally related, but it's the background energy. It's known that there's this whole background energy in the universe at all frequencies, at all times. It's like a full bucket of water. It's just waiting for you to do something to make it spill well. And all the time that's in the state. And in fact, it doesn't even have to have a drip come in for something to spill. At times this will happen on its own. But on average, the number of drips coming in and the number of drips coming out, over a long period, it's got to be more or less equal. So we've got conservation of energy, there's no question about that. I've written an article which goes through this and takes a large number of different things that are talked about in quantum physics and explains what they really mean in terms of this model. It's a simple analogy, but I think it helps to clarify the weird mystical stuff that people start thinking about quantum things.
So you certainly don't have a particle that is traveling.
No,
and this
is the nearest to a particle, the drip.
Yes,
but
and you're making the analogies in light where they attribute a singular cause and effect, which they attribute to a particle traveling. But the wave is what's causing. There is a cause and effect because of the wave, but we also have to consider that by the time it drips over the edge, it's not only the initial wave from a single drip, but it's also from the vibration of previous drips, creating waves all throughout the bucket that are adding to the overspill.
And although I said that's like a particle there, in nature there isn't anything that's really a particle. It's what's happening there is a more or less discrete event. A quantum of energy is released. It is actually just a change from one wave state to another of a standing wave. And so let's specify it again. A photon exists only as an amount of energy released at one point at one time, or an amount of energy absorbed at one point at one time, but in between there are no photons. There is no identity to the drip in between. It's just waves, it's pure waves. So in that I'm saying Feynman was wrong. He said that a photon is a particle, but there is no photon in flight. This is another analogy I make to try and explain why the interpretation of the collapse of the wave function is not meaningful. It's a statistical thing. It has nothing to do with the nature of reality. We're all familiar with that game that you used to play, that you pulled the little lever and it shot a ball up and it bounced in and it came boing, 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 boing down here. And there were win and lose holes. The win holes, of course, were right out the sides here, and all the lose holes were in here. So it was much easier to hit a lose hole. So in this case, we've got one of these, and this thing at each point it can bounce either left or right. So this is the distribution of probability that it will end up in any given place at the time it comes in at the top. Now, let's supposing at the time it comes in at the top, we turn the lights out.
Yes.
And we turn them on again when it's at the bottom. That's what we're expecting to see. It could be somewhere in there, it's higher probability in the middle and falling off at the edges. Let's supposing we do this now, we turn the lights off and it's at the top, and when it's halfway down, someone takes a flashlight picture.
Yeah.
An observation is what we call an observation. And let's suppose the flashlight shows it there, and,
Yes.
and now it's dark again. What's the probability of where it's going to end up now? Well, the centre of it has to be under that. It's now got a narrower spread here because it's got more bounces to occur.
Yeah.
Right? It can't really end up over there now, because if it bounces right 3 times it can only get to there. So now we've got this probability.
Yes.
So the wave function has changed.
Mm-hmm.
It's collapsed. But did anything happen to the little ball bouncing down?
No.
It just kept on bouncing.
Yeah.
It was bouncing before, it was bouncing afterwards.
Yeah.
So reality didn't change as a result of this. Just our information about reality changed. So in interpreting those things, it's important to understand that it's that there's more. There's what's really happening, and there's what we know about what's really happening.
Yes.
And what's really happening is a simple mechanical process. What we know about what's happening is subject to observation. Of course it is. That's what we know through observation. But it's nothing mysterious. It's not some peculiar thing that happens to nature at that point. I might add that when I went to look at the McGraw-Hill Encyclopedia of Science and Technology, it's about yay long. It's a great big encyclopedia, lots of volumes. If you look up collapse of the wave function, there's probably 2 or 3 volumes of it equivalent, or at least more than one volume that's on quantum physics spread throughout it. If you look up collapse of the wave function in the index of that, it's not there. You can do all of quantum mechanics without that, and the clever people that wrote that encyclopedia know that, but it's still taught in a lot of universities about the collapse of the wave function, which is an unnecessary idea.
Yes.
This is explained in one of the physics textbooks.
Yep.
And Milo Wolf said this is in fact more or less what happens with an electron. I showed some animated pictures of this before. What we've got here is we've got a ball, and we're going to put 6 strings on it, one going along each of the axes, or two along the x-axis, 2 along the y, 2 along the z.
Yeah.
What we then do is we rotate it by 180 degrees in place.
Yeah.
So let's suppose we've got the ball here, a string coming out. We're going to rotate it 180 degrees that way.
Yes.
Now what we're going to do is spin the ball.
Okay.
And at first you think, all these 6 strings that are going off, you think they're going to get awfully tangled.
Yeah.
Turns out they don't. The ball, it actually passes around, the strings pass around, and first of all these ones that were like that come around, and then they go the opposite side the next time, and then they go the other side next time. Alternate times around, they go opposite sides of each other, so they untangle. They never get tangled. And this is given in the physics textbook as an example of spin half rotation, because you turn it once and it's only gone halfway through what I can do. You have to spin it again, and then it's done the other half. So it's in quantum mechanics, a lot of the particles have spin half rotation. So this is a possible explanation of what's going on. Milo Wolf says that when you do this and assume that with an electron behaves like this, that it is this sort of a deformation in the ether, if you like, then it will give an explanation for all the properties of an electron.
Indeed.
I'd like to talk to you about photons, wave-particle duality, and Young's two-slit experiment, and how we should correctly interpret the results of these things. There's a lot of talk that light has a wave and a particle nature, and Feynman actually went as far as to say light is a particle. So I have to start off by saying Feynman was wrong, and that's a lot of physicists aren't going to like that, but it doesn't matter, and I'm going to explain why he was wrong and why we've gone down the wrong path with some of the stuff. So essential thing about it is, I'll give a description of what I think a photon is and what happens, and then explain why that means you shouldn't have the Feynman view. We have events where photons are created, and we have events where photons disappear. Those events are when the model is that in an atom, an electron jumps to a different orbital, or some other change in the structure of some atomic structure or nuclear structure. A photon is emitted. Somewhere else, at the same frequency, a reverse event happens of the same type, not necessarily exactly the same type, but similar, and a photon is absorbed. Now, those events, I will say, yes, they are more or less discrete events, and it makes sense to talk about emission of a photon and absorption of a photon. But in between, I don't think there's any such thing as a travelling photon. There's no such thing as a photon in flight. What there is the electromagnetic field developing according to Maxwell's equations. A photon is just something that, once it's just come out of that little bit of atom, it spreads out as a spherical wave over space, getting bigger. When we get somewhere else, that wave and other things as well have an effect which cause an event to happen, a reverse event to happen on another atom. And that event there, that wave travelling, contributed to that event in that it tipped it over the edge. And I'll talk about that separately as that I call the drip model of light, to explain that. But in effect what we're saying is it's not that photon that was emitted, but there is a causal connection between them. So we'd understand, yes, it did happen at the speed of light from there to there, but it wasn't, the photon absorbed was not the photon emitted. There is no such thing as a discrete photon in flight. There was other energy coming from the general background of waves travelling everywhere that contributed to that event as well. And this was the thing that tipped it over the edge and made it happen connected with that one. So when we have that picture of it, we can then say is a photon a particle? No, it's not. There's no particle. There's a pure wave phenomenon of Maxwell's equations developing in the motion of the light. So a photon only makes sense as an emission event or an absorption event. So once we've done that, now let's look at something like the Young's two-slit experiment. So for those that are not familiar with it, the two-slit experiment consists of having a light source, going to a thing that's got a very fine, it's a solid thing, but it's got two very fine gaps in it. Just little tiny cuts, little tiny slits. And what happens is, light being a wave phenomenon, when it comes to this, the waves coming up go through both slits. A lot of the wave gets lost hitting onto the bits that aren't slits, but there's two sources. These two slits are sources of waves coming out again. We can do the same thing in water by making some barriers and making two little holes, and we can see that the waves come out as circular wave pattern from each slit.
Yes.
If we go away from that a bit, these circular patterns are crisscrossing each other like this. So there's places where the two of them support each other, and there's places where they cancel each other out. And what we get is on the back wall there, where the light shines, we get a series of bands where they support each other, light band, dark band where they cancel each other out, light band where they support each other. We get a series of these. This thing was discovered a long time ago, and it answered the question, is light a particle or a wave, by saying light is clearly a wave phenomenon when it does this.
Are there times when it appears to go through only one slit?
Yeah, we're coming to that. It doesn't. There aren't. When you've got two slits, the pattern is always there. Right? The light went through both. Now, but people have messed with that apparatus and decided they can test some more things. So they put up something that detects whether the photon goes through this one, or detects whether the photon goes through that one, or detects whether it goes through both. I think the word detect is possibly slightly wrongly used. What they really mean is interfered with. So they're putting a detector there. If you detect it going through one, it doesn't really matter what's happening there. You've got one slit now. When you have one slit, you get a straight single band of light there, because that's the only place that it reaches when it went through the one. Now, if you put the detectors on both or on one, the results you're going to get, you need to understand something else first before you start to interpret those results. Otherwise, you can go racing off to a wrong conclusion. What you need to understand is that photons, that emitted photon that spreads out over a huge area, the proportion of the energy that's going through these two slits is minuscule. It's spread over a sphere. It might be meters away, and these little slits, it might be a fraction of a millimeter in diameter, in width. So it might be a millionth or a billionth of the energy that's going through each slit. So if you start putting detectors on the two, you've got one chance in a billion, say, of detecting it on that slit, and one chance of a billion of detecting it on that slit. So if you set a lot of photons, you're occasionally going to get one on that one, occasionally going to get one on that one, and a lot of time you're going to get none. And one time in a billion, you're going to detect it on both, and you're just going to say, oh, that was two photons, it was coincidence. As far as you're concerned, they're only going through one at a time. And that's what they do, that's the result they get. It's in my view, when you understand what a photon is and how it's spreading out, that's exactly what you'd expect to happen. Is there a way to change the experiment so that that's not what happens? Well, there is. If you get a big parabolic reflector and bounce the light off of that, you can focus the light, so instead of a billionth of the light going through each slit, you might get 10% or something like that. You might approach that sort of level. In that case, if you start detecting it at two places, there's quite a modest chance now that you will detect it at both places at the same time. And that sort of experiment can be done. Another way of doing it is with half silvered mirrors. You put light so that half of it goes through and half bounces off the mirror, and you can do things where there's interference patterns, or you can detect both. When I first suggested that this would be the result if you did this sort of experiment in the Usenet groups more than 20 years ago, people said, no, you're quite wrong, that's not what would happen. One kind fellow, I've experienced this sort of thing 3 or 4 times now, one kind fellow sent me a private email rather than discuss it in the group, because he didn't want to get in the argy-bargy of the nonsense. He sent me a private email saying, the experiment you described was done in the 1950s, and gives me a reference for it. He says, the thing that you predict is going to happen is what does happen.
Ooh.
Yeah, that a photon, an emitted photon, on average will be detected once because there's conservation of energy in the universe. But it's possible that one emitted photon will never be detected, or be detected once or twice or even more. But it's got to average once because the energy going in and coming out got to end up balancing in the long run. So we understand the two-slit experiment now, that it's the arrangement of the apparatus and the spreading out of the photon, that only a tiny bit of energy is going through each, that when you look for the particle nature, by which we really mean the absorption, when we look at it for absorption events, because that's the only time it's like a particle. It's not like a particle when it's travelling, it's a wave, pure wave phenomenon, and there is no individuality to the photon. It's mixed with all the other photons in the universe that are crisscrossing in every direction. It's just oscillations of electromagnetic field. When we look for the events where it's being detected, then we only got the probability of detecting it of what proportion of its light is going into the place where it's being detected, which is very small. And so you might think you're not going to get any events, but the thing is, this thing's emitting enormous numbers of photons that are spread all over, so you get that percentage of them. I mean, that's how our eyes work. We're only getting a tiny proportion. Everything we see, light's going off in all directions from it, and yet we can see it. Enough of it gets in our eye. There's enough of them. There's huge numbers of these things floating about. They calculate the number of photons in the universe. It's a huge number. It's more than that 10 to the 80. A lot more. Yeah.
More than long number hypothesis is accounting for.
Yes. Yeah. So that's, and I think that all of the experiments of physics can be better understood if it's recognised that there's no such thing as a particle. There's no such thing as a photon in flight. A photon, there's an event where there's emission, there's an event where there's absorption, and in between there's the electromagnetic field. And
are there times when it has been perceived that a particle is in more than one place at the same time other than the two-slit experiment?
Well, you can arrange lots of experiments where those things are happening. There's another class of experiment which might come to somewhere that you talk about. It's called the EPR, Einstein Rose and what's his name? Brodsky? I can't remember. 3 names. These guys different times talked about this experiment. And basically it's centered around the ongoing debate between Einstein and Bohr, which Bohr kept winning. But Einstein never gave up. He still believed, and I believe Einstein was right, but he never got to the thing that did it. And in this experiment, an atom changes state and emits 2 photons. There may be a different wavelength to each other, but 2 photons go out, and they then look to detect the 2. Or it may just be one that they can detect twice. The thing is, they detect this in 2 different places, and they're looking for the polarization. In the atomic structure, something does that, and the light is polarized in some direction. So they're looking for the polarization. Now let's talk about the polarization for a moment. The electromagnetic field behaves like it's a tensile ether. That means that when you move it, it wobbles this way, and light is not like sound that's compression waves going that way. It's all doing it this way. When it's traveling this way, it's wobbling this way. So what we get is that when we have something like a Polaroid glasses, we have then it's effectively it's got like that, and the light that's going this way can go through, and the light that's going that way can't.
Yeah.
So when we get polarized light, which you can get under certain circumstances with reflection things, and we look at it coming through, we see how it gets light or dark. When you get 2 of these things and put them together, if you put them like that, it looks quite light, and when you turn them like that, it's quite dark, and when you turn them somewhere in between, it's somewhere in between. One of the really fun things on that is you get 2 of them like that. If you get a third one at 45 degrees and put it on the top, nothing comes through because those 2 are blocking each other out. But if you put the 45 degree one in between the other 2, then you get something. So the order you put them, even though they're oriented the same way, you get a different result. And when you first see that, you go, what?
There's a 90-degree aspect in the waves?
Yeah. Yeah, so the wave, because what happens is, if you've got one like that and the wave's going this way, what happens is the component in that direction gets lost and the component in that direction gets kept. So what you actually get is a 70% oscillation this way.
Yeah.
So then if you hit another one at 45 degrees, it can still 70% get through. So you're down to half now, but it's still going through. So if you keep changing the angle a little bit, it can keep on going through. But if you put 90 degrees, the component that's left hits the next one and nothing gets through. Now, what's the relevance of this? They do this experiment where they're making the atomic events happening far enough apart so you can detect each one and count them in a short time, so you're not getting just random events happening in each. What they do is they've got 2 apparatuses, and they've got the detector set up with the polarizer set at the same direction, and then they change the angles a little bit, and each time they measure how many detections you get on each. Now, they do this calculation, and according to them, the quantum mechanics theory gives us a correct answer that according to the difference in angle, it's a cos squared graph, and they say that if you do the experiment with if you assume classical physics, that it would only be a cos, not a cos squared. That's wrong. It's not true. It's based on a misunderstanding of statistics, because the sample of the things that you detect, they're not allowing for that. They're assuming that they can detect an equal percentage of all events. But the fact is that if you have a photon that's coming this way, you're much more likely to detect it. At that one, it's 0, and in between it's some other value. So
but
those
it's just
ones,
as much there.
so you get one cause effect from the reduction in energy, and the other cause effect from the probability of detection, and it ends up as a cos squared. If you do the calculations with classical physics and the correct understanding, you do get that result. There's nothing mysterious, and there's a whole class of these experiments relating to that, where they try to say that by changing this polarizer here, they're influencing the probability of detection here. They're not. They're influencing the probability. They're changing the probability that they will detect it in both places, and that's all because of what they did there. Nothing to do with this. And so they think that some people think they can send information faster than light by this sort of method. by doing these things, and they talk about entanglement and all of this. The entanglement is not nature. It's the method of analysis. It's the entanglement that's in there. There's nothing mysterious going on in those things at all.
So quantum entanglement could tell us more of our perception of test results than it can of how waves are actually moving.
And it also tells us a little bit about the fact that even amongst quite bright physicists, some of them don't understand statistics fully. They understand some basic statistics, but they don't understand conditional probability, where you have a sample of things that you've got that you're looking at, and you have a subsample of that, which are the ones you're detecting, and the relationship between those depend on the experimental apparatus in both places, not just in one place. And so I don't think that there are any things that are mysterious happening in physics. I don't think that this stuff about the observer, I think I've talked already about this one where you drop a little ball in the thing and it drops on the pins, and it comes out. And this thing of the collapse of the wave function, it's not a thing that really happens in nature. It's a thing that happens. We make an observation at a point in time. Our view of it is now updated from what it was originally, and so when we do calculations forward from there, it's based on that. But the thing just carried on doing its thing. It was doing what it was going to do, whether we looked at it or not. It's not relevant.
Thank you.